Hi there, Miss Barber here. Example, given a sphere of radius 1, find the volume of the largest right circular cone that can be inscribed in the sphere. Sphere is like a beach ball. A right circular cone, think of a snow cone shell. To draw the diagram, I'll begin with a circle to represent my sphere, and then we're going to draw the cone inside it. Let's begin by sketching the base, and then we'll draw the two sides up so that we get to see a cone. Now let's go ahead and mark the height of the cone. That would be from the top where it's touching the sphere to the base of the circle, and then draw from the base of the circle to the edge of the sphere, and now we've got a right triangle. I'm going to mark the center of the sphere and know that the radius length is 1. Before we proceed, let's label some points. The bottom corner I'll label A, the center I'll label C, and the distance from the center to the sphere, that's the length of the radius, so we'll call that uppercase R equals 1. To label the height of the circular cone, that would be from the pointy end to the base of the circle, and so that length would be the height that we label H. Notice that the H can be split into two parts, the distance from A to C, and again the distance from C to the edge of the sphere. We'll call the distance from A to C Y because the distance from C to the edge of the sphere is 1. Remember, that's the radius of the sphere. And then finally, for the radius length of the base of the right circular cone, we'll just call it lowercase r. Now we have a diagram, all the parts labeled. Let's look at some relevant variables, constants, and constraints. The height of the right circular cone is the sum of the radius of the sphere and the distance from A to C. We can write that as H equals 1 plus Y. Y has to be between -1 and +1. We cannot subtract or add more than the length of the radius of the sphere. Now look at the bottom right triangle where we have the lowercase r, the lowercase y, and the uppercase r. That's a right triangle. The Pythagorean theorem applies here, and we can have r squared is equal to y squared plus 1 squared. Let's just solve for r squared. Then you'll have r squared equals 1 minus y squared. Now we're ready to get to the objective of this problem. If we want the largest volume possible, then our objective is to maximize the volume of the cone. The formula for a right circular cone's volume, that is V equals 1/3 pi r squared h. We need to have this volume function in terms of one variable. Let's make it in terms of y. R squared is 1 minus y squared, and h is 1 plus y. Making those substitutions, we will get V of y is equal to 1/3 pi, where the r squared was will replace with 1 minus y squared. Where the h was, we replace with 1 plus y. Let's multiply the terms out, and we'll end up with V of y equals 1/3 pi times the quantity 1 plus y minus y squared minus y cubed, with a domain that y is between -1 and +1 inclusive. For this function, we need to find the extrema. And to find an extrema, we always first find critical values. Remember, critical values are where the derivative v prime equals 0 or the derivative v prime does not exist. Either way, we have to find the derivative first, so let's find the derivative. V prime of y is equal to 1/3 pi and then the derivative of 1, that's 0. The derivative of y, that's 1. The derivative of negative y squared is 2y, and the derivative of y cubed, that'll give us 3y squared. We're going to factor that quadratic to two binomials, and that will give 1/3 pi times the quantity 1 minus 3y and the quantity 1 plus y. Notice that this is a polynomial, so there is no place for which the derivative will not exist. Then we're only concerned with finding where the derivative equals 0. So let's let this function equal to 0. You got 0 equals 1/3 pi times 1 minus 3y times 1 plus y. Set each of those equal to 0, and we get that the critical values are y equals 1/3 and y equals -1. Let's use the second derivative test to determine whether the critical values we obtained are minimums or maximum. Remember, the first derivative is 1/3 pi times the quantity 1 minus 2y minus 3y squared. To use the second derivative test, you need the second derivative, so we will differentiate the first derivative. This will give us v double prime of y is equal to 1/3 pi. The derivative of 1 is 0. The derivative of negative 2y is just -2. And the derivative of negative 3y squared, that's minus 6y. If you'll recall, the critical values were y equals -1 and y equals 1/3. For the second derivative test, we evaluate each critical value in the second derivative to determine whether it's positive or negative. Let's evaluate the second derivative at the value of -1. v double prime of -1, you're going to have 1/3 pi times the quantity -2 minus 6 times -1. -2 plus 6, that's a positive. If the second derivative is positive, then we know that at that point the graph is concave up. And if the graph is concave up, the most extreme point is a minimum. Let's evaluate the second derivative at the other critical value, v double prime of 1/3. You're going to have 1/3 pi times the quantity -2 minus 6 times 1/3. That's a negative. And if the second derivative is negative, then we know that the graph of the function is concave down, and that tells us that the most extreme point is a maximum. The second derivative test told us that at y equals 1/3, we get the maximum volume. Maximum volume occurs when y equals 1/3. However, the problem also said find the maximum volume, so in the original function, we need to compute it at 1/3. And v of 1/3 would be 1/3 pi times quantity 1 plus 1/3 minus 1/3 squared is 1/9 minus 1/3 cubed is 1/27. Thus, the maximum volume is 3281 pi units cubed.